Hi everyone, I feel honored to be here to introduce our paper, Oversee Outsourcing Verification to Enable Resource Sharing in Edge Environment. I'll start with the background of cloud and edge. The convenience and cheapness of cloud computing have promoted the vigorous development of Internet applications, making the explosion of the data in the network. As a result, people cannot ignore the overhead required by cloud computing to transmit large amounts of data, even with the existence of its advantages. The emergence of edge computing makes up for it. Unlike the transmission of data in cloud computing, edge computing brings computing power closer to the data, reducing the delay caused by data transmission, as shown in the figure. However, due to various considerations, the number of servers deployed by each tenant in each data center is limited. When the demand of tenants increases sharply and the resources of tenants in the edge data center are insufficient, the existing method is to forward these requests to the cloud with a lot of computing power. Obviously, this method will bring a lot of communication delay, which also blurs the difference between cloud computing and edge computing and makes edge computing lose its original meaning. Therefore, we hope to solve the problem of insufficient resources internally as much as possible. As a result, we turn our focus to the edge data center itself. The most common form of edge data center is multi-tenant data center. Each tenant purchases its own server equipment. In addition, we observe that the peak resource demand of different tenants is mostly staggered. Therefore, when a tenant is short of resources, other tenants may still have idle computing power. There are still many resources in the edge data center. Therefore, we hope that this part of tasks can be outsourced to the other tenants in the same data center, making the resources of the edge data center fully utilized. We have extracted two basic characteristics for outsourcing tasks. They are reliability and performance. Reliability refers to the task outsourced by a tenant can be executed correctly, that is, completely and without modification. This is required in the specific outsourcing environment, which is quite different from the common logic in the traditional cloud computing environment, as shown in the figure below. When a user receives the wrong results in the traditional environment, the user blames the service provider for his error, and this is reasonable, and the service provider should take his responsibility. However, in outsourcing environment, the process of which tenant A outsources the task to tenant B is transparent to the user. Therefore, when a user blames tenant A for the wrong result of the task, in fact, tenant A is innocent. Therefore, tenant A needs to ask tenant B to provide the proof of his correct execution of the task to achieve reliable task outsourcing. The second characteristic is performance, meaning that the lessee could verify whether the lessor provides sufficient resources to meet the QoS requirement according to the lease agreement between the data center tenants. Otherwise, the lessor may not use enough resources to execute the task or save power to make more profit by lowering the frequency. Even if the lessor is willing to share his system file, the file is untrusted since the lessor can modify the file information. In order to provide the guarantee of reliability and performance, we design and implement oversee an outsourcing verification scheme that enables trusted resource sharing among the data center tenants that host their respective physical servers in the same data center. It consists of two sub-schemes, the report proof mechanism and the sampling challenging mechanism. The report proof mechanism generates two certificates respectively before and after the task execution process on the basis of Intel SGX to prove that an outsourced task is executed correctly. The sampling challenging mechanism randomly inserts sampling codes or sends sampling requests to the outsourced task to verify whether the QS is satisfactory according to the lease agreement. Next, I will briefly introduce Intel SGX, which is used in your overseas. SGX is short for Software Guard Extension, which is a set of instructions that provide protected memory access control to Intel architectures. With SGX instructions, users can create an enclave running environment and execute application program in it. Hence, the enclave is loaded into the protected memory region, which higher privilege programs cannot access. Enclave environment is loaded in the file form. Users can choose to execute the enclave program locally or remotely to an untested environment. Intel SGX also provides local and remote attestation services for users to verify the correctness of the program execution. Let's magnify the process of loading an enclave file. Before the CPU loads the enclave file into the memory, it will measure the code and data in the enclave file and generate a data structure called measurement and compare the calculated measurement with the value recorded by the author of enclave after compilation. If the two values are equal, which means the file has not been modified, the CPU will load the file. Otherwise, the CPU will refuse to load. After the successful initialization, the user can use the SGX instruction to get a report signed by the CPU. We can determine whether the lessor provides reliability for outsourcing tasks with two methods, verifying the correctness of the task result or verifying the execution process. Since the results of tasks cannot be predicted, the verification of results usually depends on redundant computation, and it takes at least three times as much computing power to determine which is the right result. In addition, many tasks don't have deterministic results, such as some neural network program or cryptographic program, which will introduce random numbers. Therefore, OSC achieves reliability by verifying the execution process with the help of Intel SGX. However, it is worth noticing that only relying on Intel SGX is difficult to guarantee the completeness of task execution. The enclave process is a user process running at CPU privilege level ring 3, and hence the operating system or a privileged program has the authority to terminate the enclave process. The SGX report signed by Intel can be obtained once the enclave is initialized. Therefore, we design the report proof mechanism to ensure that enclave processes can end normally after the initialization of an enclave. Our report proof mechanism generates a pair of random keys PK SK before the task starts execution, and then embeds the public key PK into the reserved field of the SGX report. When the execution process ends, our mechanism uses the private key SK to sign the properties relevant to the execution process, including the data used by the sampling challenging mechanism and the hash of the task execution result, and generates a proof which proves the normal end of task execution. Next, we will talk about the sampling challenging mechanism. An intuitive idea to test whether the lessor provides the required QoS is to reduce the trusted environment, such as starting a monitoring process in the enclave. However, this scheme does not work due to the external calling mechanism of SGX, as shown in the figure. An enclave program runs in the chassis environment. When a system call occurs, the enclave program saves the current state and gives control to the unchassis operating system kernel by making an all call. After the operating system executes the required system call, the control is returned to the enclave. Therefore, if a monitoring process is started in an enclave, the chassis environment can only guarantee to execute system calls but cannot prove the correctness of executing system calls. Therefore, we designed the sampling challenging mechanism of ORC for performance verification. The short pieces of sampling codes are inserted into the task, and its running time will be recorded. The number of insertions and the inserting positions are random. After the execution of the task, the hash of the task result and the sample array will be recorded in the proof. If the execution time is recorded in the proof is much larger than the standard execution time, it indicates that the lessor fails to the QoS requirement. To detect the potential performance degradation of the task, the sampling code should be no less sensitive to resource contention than the actual task. The overall process is as follows. The lessee inserts short pieces of sampling codes into an empty enclave program and sends it to the lessor. The lessor pre-runs the program and returns the standard running time. If the lessee agrees with the standard running time, it will take the lease. It will make the lease agreement. Otherwise, it will consider another lessor, and then the lessee will send the outsourcing task with inserted sampling codes. The lessor executes the outsourcing enclave task and return the results and the certificates. The lessee will verify the two certificates to make sure the lessor executed and completely. Due to the randomness of the sampling procedure, it may not 100% guarantee to find a performance degradation. If it exists, we provide a formal analysis for the confidence of the sampling challenging mechanism. We can define the above problem as to determine the probability that the cheat can be detected given the sampling time, cheating time, and the actual execution time. We abstract the problem to a model of segment selection. We model the activities of cheating and sampling as selecting small disjoint segments A1, A2 to AI and B1, B2 to BJ from a long segment with length T. If segment AI and segment BJ doesn't overlap with each other, it means missing the lessor's cheating behavior. If segment AI and BJ overlap with each other, it means detecting the lessor's cheating behavior. The result is shown at the theorem. When the total number of cheating segments and the sampling segments exceeds the total length of task execution time, the detecting probability is 100%, and otherwise, the probability is like below in the formula. And we analyze the formula by bringing data. One of the most intuitive conclusions is that A and B are symmetric in the formula. The left figure shows the probability distribution when t equals 100, 200, 500, and 1000 seconds, where both A and B vary from 0 to t. The probability function monotonically increases from 0 to 1 along with the increase of either A or B. We also find that the greater t is, the more quickly the probability function converges to 1, which means a higher probability of detecting the cheat even when the sampling time and the cheating time are short. The right figure shows how the probability changes with the varying sampling time when the total execution time and the cheating time are fixed. We can conclude from the result that a cheat behavior can be easily detected with a small sampling overhead. And we have conducted our experiment on a single machine with 16 gigabyte memory and Intel Core i7 CPU. To evaluate the overhead introduced by ORC, we use three types of tasks that are high calculation, bubble sort, and Floyd algorithm, and compare these three tasks in the base mode, which is running without ORC or Intel SGX, and in the ORC mode. The experiment results show that the overhead introduced by ORC is relatively small and acceptable. That's all. Thank you.